Okay, our next speaker is Łukasz Langa. He used to live in California for 5 years, but after that time he decided to move back to Poznań because he was lacking of good pierogis and bigos in United States. Please welcome Łukasz Langa. Łukasz Langa, AsyncIO and music.
All right, thank you. Hi. Today we're going to talk about an asynchronous networking framework written in Python for Python and how we can use that networking framework to make music happen. My name is Łukasz. I come from the internet. You can find me in all sorts of places online. I'm very happy to discuss my previous Facebook employment. I'm pretty sure you have things to tell me about the company. So, of course, I do like analog synthesizers, so I'm always open to talk about this. I am serving as the release manager for Python 3.8 and 3.9. In fact, just from the hotel overlooking the university at 2 a.m. in the morning, I released Python 3.9.0 Alpha 1. So it's real. Yeah, I also built a small, humble tool that I always wanted to have, which is an opinionated code formatter called Black. You might have heard of it. So, of course, I'm happy to discuss any of those topics. Used to work at Facebook. Later, I moved back. And now I work for HDB, which is a company working on HDB, the product, which is an object relational database. Check it out. It's actually open source. You can kind of check out the code on GitHub. It's AsyncIO. It's proper Python 3.7 code. Just try it out. Today we're not going to talk about HDB though. What we're going to do is we're going to discover how AsyncIO can be used to process MIDI. If you've never heard of MIDI, you're going to learn what that is in a second. To drive hardware synthesizers. And because just talking about it would be too boring, we're going to do it live. So, as I already told you, I kind of like analog synthesizers, which is a way to make music using very simple electrical circuits. Those electrical circuits are not software driven, at least not the component that actually makes sound come out of your speakers. Those devices use very simple analog oscillators that are controlled by voltage. And if you give it more voltage, the pitch is higher. If you give it less voltage, the pitch is lower. And so literally you have to tune them. You have to do like all sorts of things for them to sound nice. However, they have this very, very pleasant retro kind of vibe, retro sound that I like. I built a bunch of synthesizers myself. This is a modular that I am sporting at home. However, it's not really lending itself very well to travel. It is rather kind of brittle and it's very cumbersome to set up after you disassemble it. So instead, what I'm bringing you today is two pieces of hardware by Novation. Those are production grade hardware synthesizers, both of them. For example, they're used by Aphex Twin for actual live performances. So these might look like they're toys because the blinking lights are very nice. However, they are actually used by real musicians, not me, but like by actual musicians, to drive actual live performances. So in this case, I have two devices with me. So the first one is the circuit, which is a standalone music groove box. It is essentially like a small musical studio on its own. We are going to be using it today as a drum machine. So that this is what we're going to do for it. And the second piece of equipment is a circuit mono station, which is a monophonic analog-based synthesizer. What that means is monophonic, it only can produce one sound at a time. It's analog, so as I said, like there's actually an analog oscillator controlled by voltage that produces sound that later is processed by a filter and a bunch of other things, which are also analog. And then it goes all the way to our speakers. We're going to be hopefully hearing some of that. And those two synthesizers are in no way connected to the computer, like in terms of audio. They are connected to a mixer I have with me that just allows both of them to just be audible with this nice cinema sound setup right here. So how is this going to work in terms of Python? How is this going to work in terms of the laptop I have in the middle? Well, I'm going to have a nicer graph in the future, but if you're dying to know, the thing is this. We're going to sequence what those devices are doing using Python, using just two USB connections, like for one device each. So those devices don't talk to one another. The laptop is not even sound connected anywhere. It doesn't make any sounds. Everything that you're going to hear comes from those hardware synths. But that's the music part. Where's the AsyncIO part? You might not know AsyncIO. It's a relatively new feature. It's a networking framework that actually is a rather different paradigm of programming from what you're used to if you're using Django, Flask, or something else. So I don't blame you if you never used AsyncIO before. So I'm just gonna teach you AsyncIO in 5 minutes. How does that sound? This is the most important slide to learn what AsyncIO does. I actually had like an entire talk at this very conference 2 years back just to explain AsyncIO. So obviously I'm not going to be able to go into too much detail right now, but it doesn't really matter. Like for what we need, we just need to understand that AsyncIO at its very core, in the very, very middle of it, it's just an event loop. That event loop takes functions, so callbacks, and runs them one after the other. Usually it runs them in response to network events. So if there is waiting data on the line, it is going to respond to it somehow. But you can also just do arbitrary computation with it just by scheduling functions to be run on the event loop. There is just one event loop on a thread. So that means those functions are called one after the other. There's no parallelism right there. There's just a simple loop that calls things, and they kind of wait for one to finish to resume and run something else. So how do you run that event loop? Well, a simple way to do this is just to say, import AsyncIO, get the event loop for the current thread, and just say run forever. Well, that's great, but that does nothing because there's nothing that we registered to happen on that event loop. So how do we do this? We're going to see that in the future, but first I wanted to show you how that event loop actually looks like in AsyncIO's own code base. That code base is open source, so it is absolutely possible for us to look at the source code and learn how it works. In fact, the implementation of AsyncIO that you have in the standard library implements the main event loop in ways that are consciously made easy to understand. That is not the most efficient event loop that you could be using. The most efficient one is called UV loop. You can find it on PyPI. You can just pip install UV loop and use that instead. That is what you should be using in production. But the event loop that comes with Python, it's made to be readable. You can literally go inside and understand how AsyncIO connects things together, why this entire thing works. And let's do that right now. If you go into the AsyncIO code base, you're going to see that in the event loop, there is literally a while loop that just loops forever, as we said in run forever. But the thing that it does inside is just trying to run things once and maybe just break if there is any kind of stop error, which might be you giving up on the program and pressing Control-C, or there might be some exception that was not handled, or any other event that makes us actually not run forever. I'm kind of, not very happy with the name run forever. It's like kind of never forever. Like, was there ever any user of AsyncIO that actually ran it forever? Like, it's kind of weird, but it's what it's called. So if we could actually run things on the event loop, how would we do this? How would we register them? You can schedule things to be run on the event loop by telling the loop that please take this function and call it later. If you're calling it later, you're saying wait at least that much time. In this case, on the first yellow line, it's 2 seconds. Or you can just say call soon, which means as soon as you're done with the thing that you're doing at the moment, please run my thing. Run the callback that you have here. Obviously, the I right there means it's just an argument to the function that we're going to be calling. So this is a way, a poor way, but a way to run things on the event loop. So that sounds great. Okay, you can see on the right side of the slide that what will actually happen on the event loop if we try to run it, there would be 3 things called, like anything of 1, anything of 2, anything of 3. 2 seconds would pass and the loop would stop because we told it to, right? So a nice stop error would be arisen and the run forever would again not run forever, in fact. So this sounds great, but AsyncIO was created to allow us to do a lot of concurrent things, to make things happen at the same time, at least perceptibly. But as I already told you, and this is true, there's just one event loop, and it runs things one after the other. So if any of the callbacks is time-consuming, it is time-intensive, everything else is going to have to wait until that particular callback is done running. So if that is true, then how can we ever achieve any sort of concurrency using AsyncIO? Well, let's start with not using regular functions, but using coroutines. What are those? You run coroutines by defining async functions. So you're going to sprinkle async and await on your code. But essentially what is happening in our callback right here is we're inserting async, which means we're having an async function, and instead of using time.sleep, we're using an coroutine version of it, which is asyncIO.sleep, and we're awaiting on that. So below you see like 3 awaits, which means things are still going to be run one after the other, and that doesn't really achieve any concurrency yet, right? But having this building block of a coroutine, what we can do is we can gather 3 callbacks in a way that they're going to be awaited on perceptibly at the same time. And if you run this, then you'll see that essentially the prints just come out at the very same time. Like it's perceptibly very quick to run. So these are the main blocks that we're going to use today. We're just going to be gathering a bunch of things. We're just going to be awaiting on a bunch of things, like, you know, and it's going to be nicely perceptibly happening at the same time. In fact, if you're wondering now that what is this sort of magic? Like how does async and await actually work? We can again just look inside Python, which is open source, and see how those things are built. So when you're creating a coroutine instance by just saying callback 1 or callback 2 or callback 3, if you're not awaiting on it, like we were on the previous slide, right? We were awaiting on callback 1. We were awaiting on callback 2. If you're just creating them instead, they're not actually running it. They're just instantiated. And what is instantiated is a task. And that task, in its init, at the very end, just says, please call soon one of the steps that I have inside. So that same call soon that I showed you at the very beginning is a building block of the coroutines. So what is that step underscore step? Again, we can look in the source code, and what we're going to see is that essentially it is running a generator until the next iteration of it. And it's doing so as long as there is no result or there's no exception. And it's just registering itself again after running at the back of the loop. So now you have to understand one thing, like coroutines are implemented as generators, which means they just live. They're not being destroyed by Python before they're done. And they are being executed until one await is found. And then the event loop is going to run something else that it has scheduled at the very same time. So this is something that is going to look something like this on a graph. We're going to run a step of the coroutine 1, a step of coroutine 2, a step of coroutine 3, and a round robin. We're going to go back to coroutine 1 because as soon as it was done with the first step, it registered itself back on the event loop, and so on and so on. So by doing so, we're no longer waiting and holding the entire interpreter hostage when we are kind of waiting for an external event to happen. Instead, we're just saying, I'm waiting, so just go ahead, do your thing. In the meantime, I'm registering myself at the back of the loop if a new thing happens to us. So that's AsyncIO for us. We're going to use await, we're going to use async functions, and we're going to gather them so that we have a perception of things happening at the same time. So what is the network protocol that we're going to talk? We're going to talk MIDI. But before we get to MIDI, I don't blame you if you're not a musician and you don't really read music, you never played an instrument. So let me show you this. In music, the most basic thing that we care about is pitch. Pitch means how high is the note that we are playing or hearing. So there is a notation that enables us to just agree between people how high a given note is. And that notation is like on the very bottom here of the slide, but it also has like, you know, nice ABC names for all the notes that you're seeing here, right? So there's C, D, E, F, G, A, B. In Poland, like you would actually say H and not B. I don't know why. But those are the basic white simple notes that we have. And there's also some more like enharmonics, like, you know, the black notes on the piano. Like, we don't care like about those at this point. What we care about is that the C, D, E, F, G notation is just telling us like, oh, this is what note that is. And like traditionally, there's going to be like C0 means it's rather low, and the key on the keyboard, C2 is going to be higher, C3 even higher. So we're just kind of adding digits to it to know which octave, like, you know, how high we are, because the notes repeat actually, right? If you ever saw a piano keyboard, the keyboard is just very regularly repeating every 8 bass notes, right? So this is exactly all that you have to understand about music for the purpose of this talk. One last thing though, in the notation below, you see this very fancy key at the very left, and there's like 2 numbers there, like 4 out of 4. That means that the bars, like the timing of that particular piece of music is counted in 4 quarter notes. We can see that they are because every 4 quarter notes, there's going to be a vertical line saying, oh, we're done with this bar. We're going to go to another bar. So this is how we organize music time-based. I guess this is all that we need for the time being. So let's move to MIDI. There are many standards about networking. There's many standards about interconnectivity between things. And MIDI is amazingly one of the standards that actually worked. People in the early 80s decided like, hey, you know what would be great if we had a way to connect 2 pieces of music hardware and have them talk to each other. So one can play notes on the other, or like they can play at the same tempo. Like they can do things together. So a standard was created, and it's still like very popular, like even like the very, very basic 1.0 versions from like 81, I think, which is basically a way for us to tell a device to do a thing like as soon as possible, like right away. In other words, it is a synchronous protocol to talk to devices one through the other. Historically, we've been using DIN5 cables for them, as you can see like right there. Those were rather flimsy to use because they're like unidirectional, meaning like one cable only informed one device about things that should happen coming out of another device. But if you wanted for this communication to be both ways, you needed a second cable for this. Like another problem was that those cables like were never really durable. They had like issues with length and how far they could go. So hopefully, like we're gonna get rid of them at some point. And today, in fact, we are already in a world where most musical hardware using MIDI is using USB cables. So this is what we're going to be using today, like with this laptop, right? Like USB cables also have this great feature of being bidirectional. So there's just one connection that enables us to communicate both ways, which is great. We're going to be using that. So okay, so like what kind of messages, what kind of packets go through those cables then? Like the protocol is super easy actually to understand, like which I'm very happy about. Like it's rather trivial to explain, and it's rather trivial to see it work in practice because it's synchronous. So there's literally messages that say, please play a note on a given channel of a given pitch with a given velocity right now. It's a synchronous protocol. Like it never schedules things like in the future. It just says, now, do it. And then if you want to kind of raise your hand from the keyboard, like stop playing a note, you just send a note off signal, stop playing that note. We have channels in the MIDI protocol so that you don't need 16 cables if there are 16 voices that a given instrument can make at the same time. That would just be too silly. So there is support for channels. And historically, the important piece is that the channel 10 is just percussion, is drums. This is what we're going to use. Like all the other channels are like whatever the devices have configured. So there's going to be note on, note off events. Like simple as that. It just goes one way. If you want to have a connection the other way, there's going to be kind of another connection where you send things in. And one particular thing that we're sending all the time is the clock signal. The clock signal tells us how fast should we be going. If we know that there's going to be 4 quarter notes per bar and we're going to be playing some music together between devices, what we need to understand and we need to agree on is how fast are we playing. So again, this is a synchronous protocol. So it's literally just sending 24 pulses per quarter note to inform devices between each other that like, this is how fast we're going. And between them, you can also just say start, which means if you have any sequence configured, if you want to do anything, do it now. And if you're sending stop, that means whatever sequence you were playing, give up, like let's have silence for now. So having all this boring theoretical knowledge now in your heads, we can go and proceed to actual like practice part, to actually see the demo of what I wanted to share like all along, what I had to have this kind of introduction so that we are on the same page. What we're going to do today is we're going to use the drum machine and we're going to use the monophonic bass synthesizer as instrument sequenced with Python from this laptop right there. So the connectivity that we're going to be using is through MIDI cables, like those are USB cables. But what we're actually going to do is Python is going to send a MIDI out signal to both of them, like one connection each. And we're going to be using, just to make it a bit harder for ourselves, but also kind of more useful for actual production use, we're going to be using the clock signal from one of those hardware synthesizers. This is actually pretty interesting because what that means is that the code that I'm going to be showing you is less of a toy than you might think. You might actually be using this to interface with other synthesizers that you have at home or keyboards or whatever else. Because you know that that code is able to go as fast as this hardware that you have does. So you can do stop, you can do start, you can slow down and speed up, and it's going to keep in sync. So that's it. Let's see some code. In fact, the main function of the program that we're going to go through fits on a single slide, so I'm just going to go ahead and before the demo part show you that right away. So we're on the same page like what the program is going to be doing. So first of all, like there is this asynchronous main function. For the first thing that we're going to be doing is we're just going to get some ports out of some MIDI library that we have. Getting that ports allow us to just kind of assign some names, assign some connections to the cables that I have on either end of the laptop, right? Like we really need to understand like where are the connections. So the API is actually very nice. Like those objects, like that I have here physically have nice names that are very easy to understand. They really map to the names of those devices. So we can just ask for a port of the circuit. We can ask for the port of the circuit monostation, and we're going to get a pair each, right? Because a USB connection is bidirectional. So once we do have this, what we can set up is a queue of MIDI messages that we're going to be getting from, say, the circuit, right? Like we said that we're going to be listening to the clock signal of a hardware synth. So this is how we're going to be doing it. We're going to have a queue where signals that the circuit is sending us is accumulating. And then we're going to be using AsyncIO to consume those things on the queue. So to do this, just as you saw in slides before, we're just getting the event loop there, right? We have the event loop object, and we can now just say, like, hey, whenever we are getting anything from the circuit, that's the last line right there, please call this function, please call this callback. And that callback, as you can see, is going to just call soon a thing on the event loop. And that thing is just put the message you just received on the queue that we have, so that coroutines on the other end can now consume it and just do nice things with it. As you can see, there is no async between the MIDI callback def, because the MIDI library that we're using is a nice Python wrapper on top of probably the most kind of production-grade MIDI library that there is, written in C++. So that library is running its own C++ thread, just looking at the signals that hardware is sending. And when it's sending it, it just allows us to register callbacks to do things. Those callbacks are not going to be running on the main Python thread, which is why we have to run call soon thread safe instead of just a regular call soon on the event loop. But that's all good enough. This is just plumbing so that now we can kind of pretend that the world is fully asynchronous from now on. It's fully AsyncIO from now on. But before we get to the nice coroutines, like let's do some more kind of chores. Let's clean up the situation. First of all, we're going to close the port that comes from the mono station. We're not going to be using any signals that that piece of hardware is sending us. The reason why we have to close it is that, as I said, C++ has its own thread where it is consuming those messages, and it would soon fill up whatever buffer it has and be very unhappy with us for not consuming it. So we are informing it right away. We won't be using information coming from this device. We're only going to be talking to that device. All right, and then we're going to have some magic data class performance that I'm going to show you soon. And we're just going to run this MIDI consumer that we're going to look at next, kind of forever. I didn't use the word forever. I don't like it, but it's what is going to happen as long as we're not pressing Control-C, as long as we're not quitting this entire endeavor. The MIDI consumer is just going to consume whatever there is on the queue and use the performance object as sort of, state for this particular program. So, of course, the most important part and most interesting part and why we are all here happens inside the MIDI consumer. So let's look at that. This is hopefully like very easy to understand, which means it also fits on a slide. Without further ado, this is it. Like it is literally another for loop, another while loop that just goes on forever, and it's just getting things off the queue and recognizing what they are. If the message that we got on the queue is a clock signal, we're just going to say that, the delta between now and the last clock signal that we had, let's just store it in the performance object. We're going to be using this to time now, right? Like we're going to be using to time the performance. If it's start, means, we actually want to play our sequence that we're going to program next. So let's create the task of the drum machine. If we are stopping, if we're going to press stop here, just cancel the drum machine, delete it, this is it. the reason why this start and stop is nice is that we are actually creating AsyncIO tasks, we're destroying them, but that also means we can arbitrarily start and stop our performance without restarting the entire program. We can just kind of react to real-time events that way. So there's a clock, there's start and stop. This is the incoming signal from the circuit that is going to tell us how fast we should be going. So the drum machine, how much code is that going to be? Is it going to be an entire slide? Maybe it's going to be more. Well, it's time to find out with the demo. Let's do it live, as I promised. So we're here. I'm not going to be saving whatever I did here. We are in the directory of the project. Just so that you know how big that project is, let me just show you the tree of it. So the project is very simple. It's called AIO, which is like AsyncIO, and tone is just tone. We're going to be making tones. The file we're going to be looking at now is just main PY. Let's just open it. Main PY right here. So the main PY file, we're going to be talking about this like in a second, but let me just make the font a bit bigger. Is that big enough? Yes, okay, cool. The performance object, as you can see, is a data class. It doesn't do much of anything. The only thing that we did to kind of have abstracted away some very boring things that happen in MIDI all the time is we created some helper functions to play a drum or to play bass, because bass is going to be this thing right here. And that play is literally a function that just sends MIDI messages. You saw the MIDI messages before, right? We can really say, like on our MIDI connection, please play a note. And then we can say, please stop playing a note. So the only reason why we have a nice play function is for us not to have to use this kind of weird bit notation all the time and whatnot, and just be able to say play on a given channel, play a note of a given pitch for this many pulses with a given volume and some other details. So that's it. And also sometimes you don't want to actually play, you just want to have a rest. You want to have silence for some amount of time. So we just have a helper function that just waits. It's just going to use AsyncIO sleep, as we saw in the example before. AsyncIO sleep for this many pulses. Okay, good enough. So now having our main function, we're going to be using UV loop because production, and we're going to be running our async main that you already saw. And we're going to have a MIDI consumer that you already saw. And this is our drum machine. I know it's a lot of code. It looks scary. But it's really all we need. If we have this, we can now start playing music. So let's see, without further ado, if any of this is going to work. So now is anything playing? No, it's not, because we didn't press start. We are clocking the performance from a hardware synthesizer. So now nothing is happening, even though you can already see that all the events going there means at all times the circuit is telling us how fast to go, 24 signals per quarter note. But we didn't press start, and we programmed before that we are only ever going to create the drum machine once we press play. So if we do, we have a rather simple performance here. It's just a while loop that is literally just playing a drum every 24 pulses, which happens to be exactly a quarter note. So that is actually pretty boring at this point. It's not very interesting, like in any way. So can we do something more impressive? Well, we can. Let's stop that thing for now and add some more code. For example, if we said that we want to play a snare drum every second note, what we're going to get instead is something just a tiny bit more interesting than what we had before. Okay, like I know I'm no Daft Punk, but like it's getting increasingly similar to actual music, doesn't it? But it's still rather kind of boring. But let me just use this opportunity for you to show you what would happen if we slow this thing down on hardware or sped it up. So as you can see, it already responds to what we're doing in hardware, which is pretty sweet. If we press stop, it stops playing. If we're pressing start, it starts playing again. Okay, there is some basis, there is some hope that there's going to be something more interesting happening soon enough. So now, obviously, we have Flake 8 yelling at us like, hey, you're creating variables and you're not using them. Like, you know, can clean up your life. So let's use those hi-hats. But what I would want to do, like if you ever saw a real drummer, like they can play the bass drum and the snare drum at the same time they're playing the hi-hats. But here I just have a while loop that doesn't do much of anything. So what can we do here? Well, how about we actually create an internal async def here saying that this is our bass drum. It's going to be our bass drum. There's going to be a while true loop here. And that's going to be the bass drum from here. Okay, cool. And then we're going to have a separate one for the snare, which is also going to just play the drum. But if we just play like this, we're just going to be hitting the bass drum and the snare drum at the very same time. Kind of know what we want. So instead, let's just say that instead we should be waiting here. And the wait should be for also 24 pulses, meaning like the snare drum is just going to wait for a hit and then hit, wait for a hit. Cool, good enough. So next thing that we're going to do is we're going to create another async def for the hi-hats. Having this now, we can just say let's play closed hi-hats twice. This is gonna be kind of simple, but more interesting than it was before. And let's play them like rather fast, and then give us some space with the open hi-hat, so the open hi-hat can actually kind of reverberate for a bit. Okay, so now we have 3 coroutines. How can we make them run together? Well, we saw already. We can just await on AsyncIO gather of those 3. So we're just going to instantiate our bass drum, we're going to instantiate our snare drum, and we're going to instantiate our hi-hats. Having those 3 things together, we're gathering those. Things should be happening. All 3 are while true loops. Things look good. Flake 8 is not yelling at me. Let's try it out. Okay, we need to press start. All right, we're hearing things happen concurrently at the same time. Why? Why is it possible? There's just one event loop on one thread. There's just one cable going to the circuit. So is it really happening in parallel? Well, no, it's not. It's just a stream of events. But if they happen close enough to one another, it is perceptibly the same thing. As you can see in the latency that I'm showing here, like it's like microsecond precision. So essentially, it is not distinguishable for a human being from being actually at the same time in parallel. All right, so we're having this thing, and it kind of doesn't sound awfully bad. Like if you are a musician, you might hear that there's something not quite right with the clock. We're going to be talking about this in a second. But for now, I just want to stop this to not bore you to death with this 4 on the floor beat. Instead, now having this, we can use Python to create some variation. And if you're creating some variation, if you're creating a project in Python that is going to be successful, what you're going to do at some point, like always, every time, you're going to be importing iter tools. That happens every time to me. So we're going to be importing iter tools, and we're going to be using it here to just play with the bass drum for a bit. For example, what if we don't want to play this bass drum at the very same volume at the same time? We just want to cycle through a bunch of volumes. So we can define those volumes. Say, one volume could be 127, another one could be like 64, another one could be 32. Or in fact, maybe we can even just do a 96 in between, so there's 4. So now instead of, yeah, Flake 8, you're right, we're not using it yet. Instead of a while true, we can just say for volume in iter tools cycle through the volumes. And having this, we can just say, please use this particular volume that we have right now. Okay, this looks good. Let's see what is gonna happen now. Nothing, because we didn't press start yet. We can hear the bass drum kind of going back and forth, but that gives me an idea. If we speed it up, that is gonna kind of sound like an echo, like reverberation. So let's do that. Let's just tell it to just go faster, not a quarter note, but half a quarter note, a 16th. So let's go there. Okay. Oh, yeah, an 8th, of course, not a 16th. Okay. Kind of sounds like echo now. But what is very interesting in kind of electronic music are polyrhythms. Polyrhythms is a very simple concept. It just means there are different things happening at the same time, counting in different times. And just having two things not being like in sync time-wise, but at the same time still like measuring the same pulses makes for very interesting sound effects. So for example, if we just remove one of them, now we just cycle through 3 steps and not 4. So just having this, let's see what interesting things we might achieve. Okay, that sounds a bit more interesting now. And we can, in fact, like maybe kind of like do some like trappy rhythm if we just slow down that snare drum as well. So if we make the snare drum slower right here by twice, this is gonna sound like more hip-hoppy now. Let's see what we can do with that. Right? And I mean, like, I'm no Jay-Z, but like it kind of starts sounding cool. So what the purpose of this exercise is to show you that like all this code is just regular Python. It's trivially easy to understand what is happening just reading it from top to bottom, and yet through the magic of the gather right here, it is playing like perceptibly at the same time, perceptibly in parallel, and like doing already a rather complex sequence. But if you're listening to it now, like, is it really in sync? Are the coroutines in sync between one another? No, they're not. This drummer is really bad. Like, things are not where we want it to be. So what is happening here is called clock drift. Clock drift happens when you are counting on a given piece of hardware the timings between pulses, and some other piece of hardware, or in our case, there's just different coroutines, are also counting pulses, but they never recheck whether we are on the same page. So they drift away, and it's clock drift. There's literally a Wikipedia page about this thing, because it is something that happens even to production hardware, and there's like very cumbersome workarounds for this. So obviously, we would not be able to use this in any sensible form if we had to like kind of bear with this unbearable back clock drift. Like that really means like, you know, we should just pick up some other career. Like, you know, we're not gonna be successful musicians with this. So instead we have to fix what we're doing with timing now to be a little smarter. But what are we doing now again? So the current way to just count how fast we should be going is just to hold the delta between 2 pulse signals that we got from this circuit. If you remember correctly, like the circuit at any given point in time, always, every day, all day, is sending us 24 pulses per quarter note. And we're just storing the timing that there was between that pulse delta, between those pulses as a delta, so that we can use it, first of all, to when we're playing, to wait for a given amount when the note is playing, and then as that note is stopping, we can wait for the rest. And same, if we are resting for the entire thing, we're not playing anything, we're also sleeping for a given amount of pulses, right? So that sounds like it should be fine, but the problem is this delta is never perfect, and the time that we are taking it might not be the perfect timing that like the device is actually sending us. So what you have to remember is this is a synchronous protocol which is sending things as they happen, and of course there's always some latency. My MacBook might decide to like start updates or whatever else. So like this is never perfect, so that will never work. But we can do something better. We can teach you something new about AsyncIO and solve this problem altogether. So let's go through this. However, there's a bit of typing involved, and I don't want to kind of like be very embarrassing like making typos here. So let me just show you what that particular thing does. For now, let's just check out whatever we have here. See, I'm terrible with typos. If we're doing second step, that's the full drums. We already saw them. We're gonna go back to like those kind of boring like techno 4 on the floor drums for the time being. And now we're introducing a metronome. What does that mean? Like how does that look? Well, in fact, there is not much happening here. We're gonna look at the metronome class in a second, but the change that we're gonna be doing is instead of holding a pulse delta as we were before, we're just gonna hold on to a metronome object, and whenever we need to wait, we're just gonna let the metronome wait for us. And for us to understand how long the metronome should be waiting, we're just gonna tick it every time that there is a clock signal. We're just gonna say tick, 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 tick. So we're no longer looking at deltas between two pulses. We are storing the ticks. And when we're starting, we're just restarting the metronome so that the starting point at the same time is also synchronized. Okay, cool. So that is essentially what is happening now. Like, in fact, see, like there's some less code that we have to do now because of this. And let's look at the metronome class. Is it scary? Is it gonna be complicated? I hope not. The metronome is another data class. I like data classes, and if you don't know data classes yet, you should be using them for everything. Like you might also use the pro version of them, which is adders, but they're the same concept. Essentially, what data classes allow you to do is to just specify a bunch of attributes, and this magic decorator is going to create a dunder init method for you. It's going to create a good dunder wrapper. It's going to create like equality, hashability, like other things for you in a correct way. It won't forget. It won't kind of update one dunder method while forgetting about another. It will always be correct and without the boilerplate. So data classes, great. What we're using it for is as well to specify nicely what types given things are. This is useful because first of all, it's documentation. Second of all, that allows us to actually kind of inform the data class creation on like what thing to expect. For example, in this case, we're saying it's just a factory of list or a factory of a lock. So every time we're going to create a metronome object, it's going to create an empty list for countdowns, and it's going to create an empty, a new countdowns lock for us. Okay, so that's data classes for us. What about the wait? The wait is using a countdown. That countdown is gonna just go down to like the 2-0 from wherever we are with the pulses that we're counting, and then it's just gonna be letting control back to AsyncIO. So with a given countdowns lock, we're just appending the number of countdowns and awaiting on them. How does this magic thing work? Like, why awaiting on countdown is taking from the number of countdowns that we should have? Well, it's actually pretty simple. Like the way it works is a countdown is an AsyncIO future. New concept. It's nothing. A future is a promise that something is going to have a return value in the future. So having a future means I don't have what you want now yet, but if you await on me, I'll let you know when it's ready. I will let you know when it's ready. So what we need to do here is simply, when we're ticking, we are ticking down on the value that we have. And if that value is 0, and we have not yet let people know that it's 0, then we're setting the result. We don't really need any result now, so we're just setting it to none. But this is how we are saying that this future is done. So if you are awaiting on a future, but it's not done yet, it doesn't have a set result, that coroutine is going to just keep waiting for it. It's just going to keep waiting for it. But as soon as the set result is done, if any coroutine was awaiting on that countdown, now it will continue. So that countdown allows us to really be synchronized with the tick. There's some just a bit of more code here, but the only thing that is happening really here is that we need a countdowns log so that if many things are happening at the same time, like we're not going to destroy the list that we have here. It's really just kind of housekeeping. But the metronome is using a concept of AsyncIO, which are futures, just to show you this line. That is the most important line, that you can await on futures. And the futures are going to kind of set a result and let the flow of that particular thing go when the result is set. And we can wait on that same countdown with many coroutines, meaning we are always gonna stay in sync. So let's see if that sounds any different now. Okay, it's pretty much in sync. Let's pick up the speed. Sounds in sync to me. And in fact, you have to believe me that like if you left it for hours, which I did testing this talk like in the past, never goes out of sync. It solves the problem perfectly because we used synchronization primitives and the simplest one that there is in AsyncIO, the future, to make sure events are happening like in unison. They're not in parallel, but they're perceptibly in parallel. All right. So having this now, you're probably wondering like, hey, he brought another instrument, but he doesn't doing anything with it. So let's introduce that one then. If we had already our consumer like react to a start by creating a drum machine task, maybe we could do the same to play the notes on this guy, on the bass synthesizer. So let's do that. To speed things up just a bit, let me cheat with Git again. So having this, what you just saw is boom. Now, next to the drum machine created at the start signal, we're also creating a bass line, right? And when we're stopping, we're saying all notes off on the drum machine, we're deleting it, and same for the bass line. We're just saying all notes off, delete the bass line. So how does the bass line look? Is it also as terribly complicated as the drum machine? Well, yes, it is. So that's our analog synth. This is what we're going to be doing with this. For now, we're just playing the C2 note over and over again. Sounds great. Let's try it. This is sound coming from the synthesizer. It's a hardware synthesizer that has many knobs. Let's try them out. So there's a filter here, there's some distortion that we can use. There's a keyboard here, I can also use that one to kind of make things more interesting. Right, okay, it's a hardware synth. The bass note is being sent dutifully by AsyncIO. Now we can do like stuff with the filter or whatever. Okay, we're gonna let them go for now. But remember, we did like some rather interesting polyrhythms with the drum machine. So can we do anything that is interesting with Python that also utilizes this and kind of build something rather complex with minimal number of lines of code? So yes, we already used iter tools, which what it gave us is cycling through things in a predictable order. But we also have the random module. We can do things that are a bit less predictable, but also funny. So without further ado, we can change this analog synthesizer to still play our keynote. That's what we were doing before, that boom, boom. And the decay here means like we're really spending all the time possible for this particular like note to play. In the real world, if you're playing the piano, you never play a full quarter note. You're never playing a full note or whatever, because you always have to just pick your hands up, do something else. In this computerized world, we can have hands that are so sticky that we're playing the full kind of amount of a quarter note. So let's have that for the time being. And then we have an arpeggiator. What arpeggiators are algorithms, devices, or pieces of software that allow us to play given notes. For example, those three that we have here, there's going to be a C, there's going to be an F, there's going to be a G, and then, do stuff with them. Like sometimes they're predictably just going through those notes in a cycle, which we're already kind of doing here. Fine, like we're going to be doing that. But we can modify things like what octave we're playing on. So maybe go higher or lower, or maybe go like change the volume. Like we're going to do that next. But for the time being, let's just see whether anything here makes sense, whether that sounds in any way interesting. But before we begin, wait. I said that this is a monophonic analog synthesizer, meaning it can only, play one sound at a time. So what does that mean for me to just have two coroutines now, to have a keynote and an arpeggiator playing at the same time? Well, every now and again, I do have a wait here, right? Means this arpeggiator is not doing anything now. So when that happens, we're just going to be playing the bass note. And when that is not happening, we're going to be playing whatever whatever arpeggiator has in stock for us, for whatever length it has for us at the time. What this allows us to do is, with synthesizers like these, you can glide between different pitches when you press two notes and hold on to them. Don't kind of let them go. So we're going to try some of that in a second as well. So let's hear this. That's kind of, getting closer to the end of the talk. So let's see what is going to happen now. There's an arpeggiator. Wow, that is, okay, cool. It's playing stuff for us. See, no hands. What I can do is, I promised you glide, so let's try some of the glide and see what it's going to do. Okay, it does glide, right, between notes. Maybe it can glide a little less. Or we can configure the tempo here, see, it's also in hardware. So this is something that actual musicians can use for actual performance to just automate things that have to happen. And MIDI is also used for visuals. It's the same very simple protocol. So you can create an entire live set doing both lights and kind of video and music just using that. But I also promised, if you actually listened to or read the description of the talk, to show you that some of the melodies that we're playing might be informed by the player. For now, I was just pressing play and just kind of being playback Mariah Carey to you. But I want to actually just play something, on the instrument and have it actually do things for me. So we can change what we have here just a tiny bit. And when we do, let's see what is different actually. What we're going to do is we're going to store the last note that was played and use that note here in the bass note instead of that C that was just the bass note that we used before. So the arpeggiator is still running on its own, but the bass note is going to be informed by me playing the circuit now. Let's see if there's any audible difference now in what we had before. There's not, because I'm not playing anything. But if I start, I hope you can hear that actually the bass is changing pitch now. The bass note is changing pitch, right? Oh, listen. It's pretty cool. All right. So what we have here is it is responding to my own input now. And what I can also do now if I think about this correctly, this is a full groove box. It's a full device that can not only just play whatever I give it, but also play sequences of its own. So what I can do now is play a stored sequence. See, no hands. It is playing what I just played before for you. And And using this opportunity that I don't have to do anything anymore, I can just go and play another synth. So just like to do what every musician wants to do and everybody is kind of groaning now, solo. All right, that was AsyncIO and Music. My name is Łukasz Langa. Thank you very much.